This episode is brought to you by Brilliant. The paper bag. It's just a bag made of paper, right? Wrong. You're dead wrong. The paper bag represents a marvel of mass production. With over 200 billion produced in 2025, it costs on average just 3 cents to bag up your groceries in paper, 6 if you double bag it. Here is the delightfully introspective, plain brown story of the paper bag. The story of the paper bag is directly intertwined with that of the Industrial Revolution. For millennia, bags were rudimentary, often handmade containers that simply could not be produced in large quantities. It would not be until the onset of the Industrial Revolution where Francis Wolle, an American schoolteacher and inventor from Pennsylvania, would be granted a patent for the first machine capable of mass-producing paper bags. His 1852 patent described a process where a piece of paper of suitable length are given out from a roll of the required width, cut off from the roll and otherwise suitably cut to the required shape, folded, their edges pasted and lapped, and formed into complete and perfect bags. The mechanism described in this patent would go on to produce bags on a scale that was previously unimaginable at 1,800 bags per hour. Quickly capitalizing on his invention, Wolle and his brother founded the Union Paper Bag Company. This company eventually became part of the Union Camp Corporation, which is now owned by International Paper, forming a direct and unbroken lineage from the very first paper bag machine to one of the world's largest packaging corporations today. While Wolle's initial design was revolutionary, it suffered from several functional limitations. The bags produced by his machine were of an envelope-style design, with a V-shaped bottom. This structure meant the bags could not stand upright on their own, presenting a major challenge for retailers. Furthermore, their narrow, tapered shape made them unsuitable for holding bulky or irregularly shaped items. The next evolution of the paper bag would solve these limitations with the incorporation of a flat bottom to the design. While James Baldwin, a paper maker from Birmingham, England, was granted a patent for an apparatus to make square-bottomed paper bags in 1853, Margaret E. Knight, one of the most prolific female inventors of the 19th century, would be credited for popularizing the flat-bottom concept. In 1867, while employed at the Columbia Paper Bag Company in Springfield, Massachusetts, Knight observed firsthand the inefficiencies of the existing V-shaped bags, and from her mechanical experience with her previous textile loom safety invention, Knight set out to improve the process. She developed a machine that could automate a more complex series of actions, feeding, cutting, folding, and gluing paper to form a square, flat bottom. By 1868, her machine was fully operational, dramatically improving the company's output and the uniformity of its products, quickly replacing the work of 30 people folding bags by hand. Knight was awarded a patent for her invention in 1871, despite an attempt at stealing rights to the design by machinist Charles Annan. From this, she would co-found the Eastern Paper Bag Company in Hartford, Connecticut, to commercialize her invention. The next innovation to the paper bag would come in 1883 from Charles Stilwell, who patented a machine that added pleated sides to the square-bottom bag, creating the self-opening sack or S.O.S. bag. This design represents the final major structural evolution that produced the modern paper bag. The addition of pleated sides or gussets allowed the bag to be folded perfectly flat, enabling them to be stored and shipped in compact stacks. Furthermore, the design lived up to its self-opening name. The pleated construction allows the bag to stand upright and remain open on its own with a simple flick of the wrist, making it even easier and faster for clerks to fill. By 1912, Walter Dubner, a grocer from St. Paul, Minnesota, would devise a simple yet transformative addition to the paper bag. Observing that customers struggled to carry multiple or heavy bags, he began experimenting with ways to reinforce them. Dubner settled on a cord to strengthen the top edge of the bag to create a pair of carrying handles. Known as the Dubner shopping bag, they were a resounding success, dramatically increasing a bag's practical load capacity to 34 kilograms or about 75 pounds. The popularity of Dubner's design grew rapidly, and by 1915, his company was selling over 1 million handled bags per year. The elevation of the paper bag to a mass-produced consumer product was directly tied to the development of Kraft paper in the 1880s. With more complex folds and creases required by Knight's and Stilwell's designs, the need for a stronger, more durable paper became apparent. Derived from the German word Kraft, meaning strength, this chemical pulping technique quickly became the dominant method used to produce the strong, durable paper required for modern packaging applications. The process begins with raw materials, primarily wood chips sourced from managed forests. While softwoods are often preferred, the Kraft process is versatile and can utilize hardwoods and even non-wood sources like bamboo. The primary objective of the process is to separate the strong cellulose fibers from lignin, the natural polymer that binds wood fibers together. The chemical conversion begins with impregnation, where wood chips, typically 12 to 25 millimeters long, are first treated with steam to expel air from their internal cavities. They are then saturated with white liquor, a hot aqueous solution of sodium hydroxide and sodium sulfide that penetrate deep into the wood's structure, initiating the breakdown of lignin. Next comes cooking, where the impregnated chips are transferred to large pressurized vessels called digesters, where they are cooked at around 170 to 180 degrees Celsius for approximately 2 hours. Under these conditions, the strongly alkaline white liquor effectively dissolves the lignin and hemicellulose, freeing the cellulose fibers without significantly shortening or weakening them. This preservation of fiber length is the primary reason for Kraft paper's superior strength compared to paper made via other methods. After cooking, the mixture consists of solid cellulose pulp and a liquid byproduct known as black liquor, which contains the dissolved lignin, chemicals, and other wood components. The pulp at this stage, called brown stock, is thoroughly washed to remove the black liquor and other impurities. It is then refined to achieve the desired consistency for paper making. For the classic brown paper bag, this unbleached pulp is used directly. If white paper is desired, the pulp undergoes additional bleaching stages. Modern paper bag production starts with this pulp slurry. It's first spread onto large moving mesh screens to form a continuous wet sheet. The sheet is then passed through a series of heavy rollers to squeeze out excess water, followed by heated cylinders that dry the paper to a final moisture content of 4 to 8%. To make paper more porous and elastic, a technique called microcraping is used in the drying process. This is done by creating microscopic wrinkles or folds in the paper by drying the paper with very little tension, which allows the fibers to shrink and bunch up naturally. This process gives the paper a built-in ability to stretch before it breaks by 4% along the direction of its production and up to 10% across its width. Machine direction elongation can be further improved by pressing between very elastic cylinders, causing even more microcraping. The paper may be further coated with polyethylene or different dispersions to create a barrier to moisture, oils, or bacteria. The final paper is then wound into massive rolls. Higher quality paper bags made for more demanding packaging are made from virgin Kraft paper pulp, while pulp containing recycled material is used for lighter applications. The large roll of Kraft paper is mounted on a holder, and a system of rollers unwinds the paper and feeds it into a machine at a constant, controlled speed and tension. For brands or customized bags, an inline printing unit is integrated into the line. Flexographic printing is the most common method, using flexible photopolymer plates to transfer fast-drying, water-based inks onto the paper surface in multiple colors. The printing occurs on the flat paper web before it's folded. The printed paper web proceeds immediately through a series of formers and rollers that folds the paper into a continuous, flat, or gusseted tube. In this process, a precision gluing system applies a line of adhesive, typically a fast-drying hot melt glue, along one edge of the paper web just before it's folded into a tube, creating the bag's longitudinal seam. This gluing system's precision is vital to ensure a strong bond without excess glue that could cause bags to stick together. The continuous paper tube is then fed into a cutting and bottoming section. A rotary cutter or guillotine-style blade separates the tube into individual bag lengths. Immediately following the cut, a complex and highly synchronized sequence of mechanical guides, folders, and rollers performs the intricate fold required to form the square bottom. Another application of glue seals the bottom flaps, completing the bag's basic structure. For shopping bags, a separate unit manufactures and attaches the handles. This is done by typically taking a smaller roll of paper and twisting or folding them to create either twisted cord or flat strap handles, and then uses strong adhesives to affix them securely to the bag body. The modern paper bag is not an arbitrary product, but rather a highly specified and regulated item. Its production is governed by a framework of standards that dictate its material properties, its safety for the intended application, and its environmental sustainability. Optimizing for one of these areas can often create challenges in another, forcing producers and their clients to make strategic choices based on the bag's intended use. These challenges are further compounded by the need for quality control within a high-speed manufacturing environment. One of the most important characteristics of a paper bag is its ability to hold weight without tearing. This is primarily determined by the physical properties of the paper from which it's made and is known as the basis weight. Basis weight is the standard industry measure of a paper's mass per unit of area, which directly correlates to its thickness and sturdiness. In the United States, it is defined as the weight in pounds of a ream of 500 sheets of paper cut to a standard size. The metric equivalent used internationally is grams per square meter, or GSM. Lightweight paper bags in the 20 to 40 pound ranges are used for applications where high strength is not the primary concern, such as with small merchandise bags, bakery and sandwich bags, and concession bags. Medium weight bags in the range of 50 to 60 pounds typically form the standard self-opening sack grocery bags and for standard takeout food bags. Heavyweight bags in the range of 63 to 105 pounds and higher are found in handled shopping bags used in department stores. The most robust bags are paper shipping mailers, which can be made from 105-pound paper or 2 layers of 80-pound paper laminated together. A bag's ultimate load capacity is a function of not only its basis weight, but also its structural design and features. For example, a square bottom design provides greater stability and strength than a flat or pinch bottom bag. The type of handle is also critical. Twisted paper handles are the strongest, capable of supporting up to 10 kilograms, while flat paper handles are the most cost-effective, but typically hold up to only 5 kilograms. Die-cut handles are the weakest unless reinforced. While there are no universally mandated official standards for paper bag dimensions, the industry operates on a set of commonly accepted sizing conventions. These sizes are often categorized by the bag's intended use, such as for retail, groceries, or food service. Paper bag dimensions are typically given as width by gusset by height. One prevalent industry standard for bags in food service and grocery applications is the self-opening sack sizing system. These sizes are denoted by a pound rating, which historically corresponds to the amount of sugar the bag could hold. It should be noted that a standard paper grocery bag is typically sized to hold around 14 grocery items, compared to approximately 10 for a standard plastic bag. For industrial applications, paper bags are commonly referred to as sacks. There are two basic designs of industrial bags: open mouth bags and valve bags. An open mouth bag is a tube of paper plies with a bottom end sealed. The bag is filled through the open mouth and then closed by stitching, adhesive, or tape. Valve sacks, in contrast, have both ends closed and are filled through a valve. These bags also incorporate several layers of paper, with some having a plastic film, foil, or a polyethylene-coated paper layer in between, forming a moisture, chemical, or pest barrier. In the United States, Code of Federal Regulations sets specific standards for industrial multi-wall paper bags used in shipping. For industrial bags, Title 49, Section 178.521 defines Code 5M1 for multi-wall and 5M2 for multi-wall water-resistant bags. These regulations mandate that bags must be constructed from high-strength Kraft paper with a minimum of 3 plies, and all seams and closures must be sift-proof and not allow powdered material to work its way out. For 5M2 bags, the code details specific requirements for making the bag waterproof, such as using a water-resistant ply or an internal barrier to protect moisture-sensitive contents. The regulations also set a maximum net mass for these bags at 50 kilograms or 110 pounds. A European equivalent to U.S. regulations exists within the European Agreement concerning the international carriage of dangerous goods by road standards under Part 6, Chapter 6.1. Both U.S. and European ADR are harmonized under the globally recognized UN model regulations. Both industrial and consumer paper bag runs are commonly quality controlled using a handful of standard tests. Burst testing strength measures the hydrostatic pressure required to rupture a paper bag sample. Peel strength test measures the force required to separate two surfaces bonded by an adhesive. Tearing strength test measures the resistance of paper to the propagation of an existing tear. Cobb sizing test measures the mass of water absorbed by the paper surface in a specified time, and load-bearing capacity tests, a functioning test where a bag is filled with increasing weight until a point of failure. Food-grade paper bags follow even stricter compliance requirements. In the US, any paper bag intended for direct food contact must comply with FDA 21 CFR 176.170 for contact with aqueous and fatty foods and 176.180 for contact with dry foods. Similarly, in the European Union, Regulation EC 1935 requires that all food contact materials be safe and not alter the composition of the food. Both regulatory bodies require that food-grade bags be made from 100% virgin pulp in order to avoid potential contaminants often found in recycled paper streams, such as residues from printing inks, adhesives, BPA, or phthalates. Additionally, all ink used must be water or vegetable-based inks that are free of heavy metals and have low migration properties. Adhesives must also be starch-based. Any coating used for grease or moisture resistance must also be compliant with food contact regulations. Today, the paper bag has become a symbol of consumer environmental awareness, being promoted as a biodegradable and renewable alternative to plastic. However, the reality is much more contentious. Manufacturing a paper bag consumes significantly more water and energy and generates higher greenhouse gas emissions compared to its plastic counterpart. For instance, making 1,000 paper bags requires over 1,000 gallons of water compared to just 39 gallons for the same number of plastic bags. Their benefits only appear after being used, as they do biodegrade relatively quickly and have a high recycling rate, often exceeding 85%. In comparison, plastic bags are derived from non-renewable petroleum, persist in the environment for centuries, break down into harmful microplastics, and have a recycling rate of only about 10%. This creates a break-even point where a single paper bag must be reused to offset its initial environmental impact compared to a single-use plastic bag. This break-even point of reuse is highly debated, with estimates ranging from 3 to over 40 reuses. This trade-off has also led to a phenomenon known as problem transfer, where legislative bans on plastic bags causes a massive shift to paper, swapping the issue of plastic pollution for the problems of high water and energy consumption. Ultimately, the issues of sustainability are derived from the single-use nature of consumer packaging. Still, in response to this environmental scrutiny and consumer demand, the paper industry is innovating with more sustainable manufacturing processes. Furthermore, third-party certifications like the Forest Stewardship Council and Sustainable Forestry Initiative provide verifiable assurance through a rigorous chain of custody tracking system that the wood fiber used originates from responsibly managed forests, addressing concerns at the very start of the bag's life cycle. The future of the paper bag is being actively reshaped by a focus on both sustainable sourcing and enhanced performance. Innovations in materials such as increasing the use of recycled content and exploring novel agro-waste fibers are fundamentally reducing the bag's environmental footprint from the start. Simultaneously, the development of advanced eco-friendly barrier coatings such as water-based acrylics, biowaxes, and PHA biopolymers are overcoming the paper bag's traditional weaknesses. These advancements are not merely incremental, they represent a decisive shift away from problematic plastics and persistent chemicals, paving the way for a new generation of paper packaging that is not only renewable and recyclable, but also robust enough to meet a wider range of modern consumer demands. Taking a simple concept, refining it, and scaling it into a mass-produced solution for several problems simultaneously is a fundamental engine of progress. If you want to sharpen your own ability for that kind of methodical problem-solving, Brilliant is where you should start. Brilliant is designed to sharpen your ability as a thinker and problem solver, using thousands of visual, interactive lessons in math, science, and AI. Its power lies in its core philosophy, active problem solving. This methodical approach is proven to be 6 times more effective than passively watching lectures, focusing on building your skills, not just observing. Instead of just telling you how something works, Brilliant has you play with the concepts yourself. You're constantly solving puzzles and experimenting with ideas, which help you build a true understanding from the ground up. This way, you're not just memorizing facts, you're building real-world applicable skills. And because all the content is crafted by an award-winning team from places like MIT, Caltech, and Google, you know you're learning from the best. Brilliant is also effortless to integrate into your day. During a commute or a coffee break, I can jump into a quick lesson listen and actually learn something new instead of just scrolling. It's the first learning habit that has truly stuck with me. A great place to start your journey is with Brilliant's scientific thinking courses. It's a great way to embrace problem solving using the physical properties that shape our physical world. To learn for free on Brilliant, go to brilliant.org/newmind, scan the QR code on screen, or click on the link in the description below. Brilliant's also giving our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant.